Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Last week at the TensorFlow Developer Summit, I met a bunch of listeners, including several who've been listening for quite a long time. One of them mentioned that one of the things he misses is giveaways, and he's right. It's been way too long since we've done a giveaway here on the show. Little did he know, though, that we had one in the works that we're excited to kick off today. The O'Reilly Artificial Intelligence Conference is returning to New York in April, and we have one free conference pass ready to give away to a lucky listener. To enter, first go to twimlai.com/AINY giveaway to access the entry form. Next, choose any or all of the 9 ways to enter. The more entries you earn, the higher your chances to win. And finally, for 3 bonus entries, answer the question at the bottom of the entry box. The giveaway ends soon, so be sure to get your entries in while you can. Now, about today's show. We're joined by Kevin Tran, PhD student in the Department of Chemical Engineering at Carnegie Mellon University. Kevin's research focuses on creating and using active learning workflows to perform density functional theory, or DFT, simulations, which are used to screen for new catalysts for a myriad of materials applications. In our conversation, we explore the challenges surrounding one such application, the creation of renewable energy fuel cells, which is discussed in his recent Nature paper, Active Learning Across Intermetallics to Guide Discovery of Electrocatalysts for CO2 Reduction and H2 Evolution. We dig into the role and need for good catalysts in this application, the role that quantum mechanics plays in finding them, and how Kevin uses machine learning and optimization to predict electrocatalyst performance. Okay, let's do it. All right, everyone, I am on the line with Kevin Tran. Kevin is a PhD student in the Department of Chemical Engineering at Carnegie Mellon University. Kevin, welcome to This Week in Machine Learning and AI.
Thank you for having me, Sam.
So Kevin, you're in chemical engineering. You've practiced chemical engineering. How did you come to get involved in the application of machine learning?
I kind of fell into it with the research that I'm doing. And so we are looking for new materials, and we need an intelligent way to screen them. And machine learning is actually one of the tools that we found that apparently does that pretty well.
You're using that in your graduate work. Have you used machine learning prior to grad school?
I have not, actually. So everything that we're doing now is kind of learned on the spot, so to say. And so it's new for us, and we still have a lot of room for improvement, but so far it's working pretty well.
Awesome. So tell us a little bit about the problem that you're trying to solve there.
Yeah, so at a high level, it's really about sustainable energy, right? And that's actually the reason that I started doing this research. And so the idea is to help make what we call solar fuels and solar chemicals. So what that means is we take energy derived from the sun. So let's say solar cells. And one of the problems right now is that when we take solar cells and make electricity out of that, if we have a lot generated during the day and we can't use it, then it's kind of wasted, right? So there are a lot of people doing really nice research into figuring out how to store that energy. Batteries is one method. The method that we are interested in is storing it in chemical bonds. So what we would do is we would take something like carbon dioxide and water, take that and the electricity we get from the sun and convert that into more valuable fuels or chemicals like methane or ethylene or hydrogen. And then in turn, we can use those for whatever application that we want. And so part of that problem to actually turn those chemicals into more valuable chemicals is that we need good catalysts to do so. And right now, our research focuses on finding a good catalyst to do those reactions. And it involves a lot of computer simulations that we have to do intelligently. And so we're using machine learning to help us decide which simulations to do iteratively.
Okay. So to dig into that a little bit more, you're trying to store solar energy in chemical bonds. In some ways, that sounds a little bit like what a battery is doing. Also,
Yeah, it's
it's
very similar.
fundamentally a chemical thing. Or you could, while the sun is up, use the solar energy to kind of power some chemical reaction, and that's kind of where your need for some kind of catalyst comes into play.
Yeah, yeah, exactly. So the setup we have actually looks very similar to a battery, right? Or the physical setups. And so if you think of a car battery, right?
Mm-hmm.
It it has a solution and it has an anode and a cathode, as in more or less two metal rods on either end, and it can either generate electricity or it can you can put electricity into it to store that energy in more or less chemical form. And so our system, what it does is instead of storing the energy in the battery itself, it generates methane and fuels from carbon dioxide and the water that is in the battery itself. Or in this case, it's the electrical chemical cell.
You just described it as an electrical chemical cell,
Yes.
and so it's not like you could use that energy to power some kind of machine to extract some other compound or fuel, but rather you're doing this all chemically.
Yes. Yep. That's the idea. The issue there is in order to perform that reaction on a large scale that could help a lot of people, we need it to be fast and efficient and affordable. And the catalysts that we have right now can meet some of those criteria, but not a lot of them. And so we're looking for more materials that we can scale up to a commercial scale. And that's the problem we have right now.
In order to do this, you need these catalysts. How do you measure the performance of one of these catalysts?
Yeah, so there are a lot of metrics for performance that experimentals usually look at, one of which we call it activity, but the idea is how fast it can actually drive the reaction. So let's say one catalyst can transform 1 kilojoule of energy and it would take maybe a few seconds, and another catalyst, it could take hours. So we want the catalyst that could takes it a few seconds to actually do that reaction. Another example is the efficiency. So just because you put 1 kilojoule of energy in does not mean you get 1 kilojoule out. It's often much less than that. And so certain catalysts are more efficient about transferring that energy than others. And there's often a balance between those two and even other properties such as how expensive the material is, right? And so there's a lot of things that we plan to play with and look at, but the work we have right now, since we're just starting out, only looks at the first thing that I mentioned, which is how fast the reaction can go.
What's the space of possible catalysts look like?
It's a good question. So one of the issues that the field has right now is that in order to solve this problem, we're more or less looking at most of the periodic table, right? And so there are a lot of elements there, a lot of iterations that go through. And even if you choose, let's say, two metals, there's still the question of what ratio do you have between those two metals, right? What if you have three metals? What ratios do you have there? And so what we have is a really rough first pass of looking at two or three metal combinations, sometimes four, for about 30 different elements on the periodic table for select combinations of ratios between them.
And so in that sense, it sounds kind of like a constrained optimization type of a problem. You're trying to figure out how to get the greatest yield from this set of materials that you're working with.
Yeah, exactly. And it's kind of a difficult problem because the search space explodes geometrically as you add more materials, right? And more composition blends. And so what we have is, even though it feels large and seems large to us, it's really the tip of the iceberg of what we could do, right?
At what level are you modeling this? Like, are you modeling this at, and forgive my ignorance here if I'm not asking this correctly, but are you kind of, when you're searching for high yield catalysts, are you modeling atomic interactions, subatomic interactions, molecular interactions, or could you do all of this, what you need at the level of, just kind of the things you might see on a periodic table?
Yeah, yeah. So what we are doing specifically is modeling things at the atomic level. And so there's a type of theory in chemistry. It's called density functional theory. So what this does, it more or less uses quantum mechanics to take a set of atoms and predict the properties of those atoms. And using those properties, those are actually indicative of the performance of the catalyst. And so we take a catalyst, we perform density functional theory simulations, really, around how the atoms interact with each other. And that will tell us if that catalyst or those atoms really will perform well in an electrochemical cell.
And so how long do these simulations take to run?
The issue here is that these simulations take anywhere from hours to days, or the big ones, sometimes even weeks to run a single one.
Oh, wow. Can you give us a high level understanding of how these DFT simulations work? What are they doing to determine ultimately whether these catalysts are going to be high yield?
Yeah. So to answer that, we can back up a second to talk about how the catalysts work. So let's take, for example, we want to turn carbon dioxide into methane, right? So it's CO2 going to CH4. That doesn't happen in one step. It happens in a series of chemical reactions. And we know from chemistry experts that the elementary reaction, we call it, the small reaction that matters most to convert CO2 to methane, is actually adding one hydrogen onto carbon monoxide. And so what that means is how strongly that carbon monoxide binds onto the catalyst is really important. So let's say carbon monoxide binds onto the catalyst very strongly, so it will react quickly. But once it's done reacting, it'll actually just stay there, never come off, and you will never actually have any product. Conversely, if carbon monoxide binds too weakly, it will never go onto the catalyst in the first place, and therefore it will never react. So there's kind of a Goldilocks effect where the catalyst needs to have a sweet spot of energy in the middle. So that's where density functional theory comes in. We call it DFT. And so given a configuration of atoms and how the carbon monoxide is sitting on a surface of a catalyst, DFT can tell us how strongly that carbon monoxide is sticking to the surface. And that is indicative of how well it's going to perform.
Presumably you're using a simulator because the laws that govern this are either too ill defined to apply directly or are at too granular a level to apply directly?
That's interesting. So when we call them simulations, we just say that because it's what it feels like. But what we're actually using is quantum mechanics. And so we know the laws that govern how everything interacts. The reason it takes so long is because it's really just a math problem, solving a lot of partial differential equations simultaneously. And that just takes a really long time.
You recently published a paper on your work in this field in Nature Catalysis, and you're using active learning to help solve this problem. Where does active learning come into play?
Yeah. So we have a set of elements that we want to look at, right? And they can have different varying composition space, as we talked about before. And we want to actually keep running simulations to keep finding new materials for experimentalists to test out. So our whole workflow is designed around the idea of we want to continuously find new materials for other people to look at. So that's where the active part comes in, because it feels almost iterative, right? So the more simulations we have, the more data we have, and the more data we have, the more we get a better idea of which sites to perform next. So in this case, what we're doing is, let's say we start out with a small database of a few hundred simulations. We use machine learning on those as a training set. And from there, we can predict how well the other catalysts that we have not simulated are, how well they will perform. And once we have an idea of that, we can pick the ones that we think will perform well as per the machine learning model, and actually just do those simulations, get more data, and then perform the regressions again and just continue that loop. And that's how we're using active learning in a sense to find new materials.
You've got this database of materials that you've run these simulations on, and they're characterized by their different kind of material properties. And well, actually, maybe you can talk a little bit about how they're characterized. Are they, is it strictly at the atomic level, or are there other material properties that you're using to ultimately become features in your machine learning models?
Yeah, so what we do is we look at the location of where the carbon monoxide is sitting on the surface. So if you can imagine how the atoms are set up, the carbon monoxide could be bonded to, let's say, one platinum atom on the surface, and that platinum atom could be bound to maybe 8 other platinum atoms. So what we feed as features to our regression model is how many atoms that the carbon monoxide is bound to. So in this case, it'll be one platinum. How many atoms that are in the next nearest neighbor or the next outer shell. So in this case, it'll be 8 platinums. We also look at the identity, the chemical identity of those atoms. So in this case, it'll be platinum. If there's more than one metal, we consider, let's say it's platinum and aluminum. We consider the aluminum too. We also look at the chemical properties of those elements. So platinum and aluminum have what we call electronegativity, which is how much they like electrons. And we look at that. And we also look at what we call the atomic number, so where it is on the periodic table. And one of the interesting features that we have is the average binding energy of that adsorbate on the material. So in this sense, let's say we already have a database of maybe 20 calculations of platinum, and we take an average of those binding energies, and that number is associated with platinum. It kind of gives a feel for how strongly it binds to platinum in general. But we take that number and we feed it into our alloys. And so when we have a material that has aluminum platinum, it has a feel for how strongly it binds to platinum and aluminum. And it sort of averages those together in a way when we do the regression.
Okay, and that's that number that you described earlier as wanting to have that Goldilocks effect. That one needs to be kind of just right.
Exactly, yeah.
And so you've got all of these as features that come out of the materials that you're using. The simulations themselves, are those only used as your labels, your answers, or are you also gaining information from those simulations that you're using as feature input?
So the simulations that we're performing effectively give us the labels for our regression models. At the same time, so those labels are the binding energy of carbon monoxide on a particular site on a catalyst. A site being a location where the carbon monoxide could just attach onto the catalyst.
I was mainly curious whether the simulation was just giving you that, that answer, that binding energy that you use as labels, or if the simulation was also kind of illuminating other characteristics of the material pairs or combinations, either qualitatively or quantitatively, that you could also use as, input signal.
Sure. So the simulations themselves really just give us the labels. If we want to look for more holistic information around what materials might work well, we actually just look at our database of simulations. So I guess for each individual one, we don't really glean much chemical information from that, but from seeing patterns arise in how many simulations work well given a certain alloy, we glean information from there.
You've got this regression model that essentially allows you to take unknown combinations of materials and guess what the binding energy will be without running through these really long simulations. Is that kind of the general goal there?
Yeah, exactly. So that's what our surrogate model is doing, our machine learning model.
Yep. And then you're using that to allow you to kind of constrain the search space for new elements. How do you tie that surrogate model into the active learning piece, or the piece that you're using to constrain your search space?
Yeah, so the very naive way to do this is to take the model evaluate it across our entire search space and pick the materials and the absorption sites that actually would work best. But there's the idea,
and if I can interrupt, that
sure,
should even be an improvement over running these simulations every time, right?
yeah, it's an intelligent way of doing the simulations, right? So what people do in the current field is they use their intuition to decide what materials to simulate next. Where here we're actually using machine learning predictions to make that decision instead of human intuition.
How well do you trust the surrogate model? When you run it and it tells you that something should have this kind of just right bonding energy, do you trust it, or do you use that to determine what you should actually simulate?
So that's a really good question. At the current state of the model, I trust it with a grain of salt, right? If that makes sense.
Mm-hmm.
But what I really trust are the simulations.
Mm-hmm.
And so the whole point of our workflow isn't necessarily to make a machine learning model that can predict everything perfectly. It's really to have the machine learning model decide what simulations to run next, which will build our database in an intelligent way.
Right. And so you were starting to walk through that process and how you applied the machine learning given your surrogate model.
Yeah. And so I think we discussed the naive way to do it, which is to use the model to find the best candidate and to just run that. But if you do that, there's the idea of exploration versus exploitation. I'm not sure if you're familiar with.
Mm-hmm. Yeah, we talk about that quite a bit on the show.
Yeah. And so that's pure exploitation. And so there's a decent amount of research into ways to balance the two. For our workflow, we had a quick and dirty way to try and balance this, where we actually made a Gaussian distribution that is centered at our optimal point, right? So let's say our optimal point is maybe 0.1 for the binding energy. So we made a Gaussian distribution centered there with a certain standard deviation. And for our search space, we use that distribution to assign a probability of selecting a new candidate material to simulate. So let's say if something was at 0.1, or the model thought it was exactly at 0.1 or optimal, then it would assign the highest probability to picking that. And the further out you go from that space, the lower the probability gets. And so once we assign an array of probabilities to our possible search space, then we just pick them at random. So in a way, we would focus on the area that we're interested in, but still, in a way, stochastically choose other materials that we might not normally choose.
Thus retaining some of that explore characteristic.
Exactly, yeah.
Okay, and then the active learning piece of this is what specifically?
So the active learning piece is the process of iteratively deciding new points to simulate for us, right? And so we have this loop constantly going. So the active part is the fact that we're doing a regression and then a prediction and then a query or simulation in our case to get us more data, which yields another regression, et cetera, et cetera. So the active part is the iterative nature of our workflow.
So you're running this kind of in serial, and then each time you produce this distribution of possible materials to simulate based on the test that you've done previously. You pick one, you run that, and then you, based on the result, you put that in your distribution. You pick another one, you run that, and you keep feeding these results back into your database, your distribution of things to try.
Exactly.
Oh, very cool. And so how do you characterize the results that you saw with the paper?
Yeah, and so that's an interesting question because we've been playing around with different methods to actually analyze our database. So we our main three methods that we thought of, we actually put inside the paper. One is to just make a list of materials that are within an acceptable range of performance and give that to experimentalists. And so we have that in the paper. Another way is to create almost a heat map, a two-dimensional heat map of what materials would work well. So on one axis would be one set of elements, so aluminum, platinum, gold, copper, and the other axis is those same elements. And so each point would be a blend of those elements. So the grid would be maybe choose copper and aluminum, and from there we can color code the grid according to the fraction of the binding sites that would work well. And so that was one other way that we could look at it. And the third way is actually simply using t-SNE to cluster all of the points that we've done simulations on, and then color code them by their energy and look for clusters that have the appropriate energy for us, and look for the themes within those clusters and recommend that those materials be studied.
And so you've got these three methods. How do you know that this method is helping you? Are you able to, ultimately, is it the number of kind of candidate combinations that you're able to find per unit of your own time as a researcher, or is there some other kind of fundamental measure here?
Yeah, that's a good question. The two that I kind of lean towards are the number of candidates we find over time. So we actually have a plot of that in the paper as well. And over time, we can see that number rising and waxing and waning according to the way we modify our workflow. The other way is really, I guess, the real way is to see if any of the candidates we have actually work and in an experimental setup. And so for that case, experimental validation, we do have collaborators that are testing some of these materials. And we actually have another paper in review right now where our collaborators tested one of the things that we've suspected to be performing well. And it turns out it did. And so that worked out perfectly in our minds. And so we're really excited to get that paper out. And you might be seeing that in the next few months or so.
Nice. And it doesn't sound like it would be enough to just demonstrate one. There's some notion of kind of demonstrating that this is a, more efficient or more repeatable process than, what folks usually do. And that goes back to, have you produced enough candidates and had those go through the experimental process in order to be able to make claims around that?
Yeah. So this is the candidates that we found so far. We found them relatively recently. So we are still in the process of testing them with experimental collaborators. One thing that does make us feel better about our workflow is that I'd say on the order of 40 to 60% of the candidates that we have found have already been shown in the literature to work well for what we're looking for, but ended up not being used for other reasons that we're not looking at right now. And so that kind of gives us a gut check to say that, hey, the things that our workflow are finding are things that people have already looked at. And so hopefully the things that we haven't experimentally tested yet might be good candidates too.
Oh, that's right, because you're only looking at one of many important categories that you need to, or properties that you need to consider to actually commercialize something. So your workflow is spitting out candidates that, according to your criteria, are good ones, but may have already been proven to be not commercially viable for other reasons.
Exactly. And so that's where some of our research might be going in the future, to start looking at those other properties as well, so that we can really trim down our list and reduce the chances of giving a bad recommendation to an experimentalist.
And so how do you envision scaling your workflow to these multiple criteria?
So that's something that we're actually looking into now. And we're still scoping that out. But the rough idea is to find the Pareto front of multiple objectives and to try and balance where we want to be on that Pareto front, if you're familiar with that term.
Elaborate on that. How do you go about doing that practically?
Yeah, so practically, we would first have to find another property that we'd be interested in. Let's say stability of the catalyst, or how long it'll stay there. Because if a catalyst operates for a few hours and then degrades into something else and stops working, then that's not a good catalyst, right?
Mm-hmm.
So that's one of the things that we might be looking into in the future. And our simulations can actually get a handle on how stable something is. And so what we would do is we would have a metric for what we call activity, or how fast the reaction goes, and we would have a metric for stability. And for all the candidates that we want to look at, we could evaluate how well it performs in each. And I mean, there's no free lunch, right? And so each candidate is probably going to perform well on one and maybe not for the other. And so what we call our Pareto front is where, let's say, you have a certain activity, right? And you find, let's say you want to have the ideal activity of 0.1. We can find the candidates that have that ideal activity, but also are the most stable. And so that'll give us one answer for that particular activity. And then we can take a step to say, okay, let's look around materials that have an activity of 0.2, a little further away. And of that, find the subset that are the most stable. And then we can continue that across the spectrum of activities and find a list of materials that are active and generally more stable than other candidates. And we would still get a list from there, but using that we could down select our material set even further.
What else do you plan on doing to kind of further this research line?
Yeah, so other things we're looking at are more intelligent ways to select the next experiments or the next simulations. And so what I told you was the Gaussian selection.
Mm-hmm.
So right now we're actually having conversations with machine learning people at Carnegie Mellon University to figure out what type of algorithms might be best suited for our application. So there's that. And another way is to actually simply improve the regression methods that we're using right now to see if we can get better surrogate models that can be more intelligent about what to select and have a better prediction rate.
With the first of those, kind of an alternative to Gaussian selection, is there some intuition that you're pursuing as to what methods might be better, or what might the characteristics of better methods be?
Yeah, so again, this is something that we're just starting to dabble in, and so we haven't really fleshed the ideas out. But a lot of the active learning literature that we've seen so far is really centered around Bayesian prediction and processes. And so that's something that we might look into to model our system with and maybe start selecting new candidates with.
And on the second direction that you mentioned, improved models, what are you thinking there? Or what directions are you looking at?
Yeah, so that kind of has an interaction with the other things we're looking at. Like I said, if we end up using Bayesian statistics to do the active learning, well, then that means our regression is going to be Bayesian based.
Mm-hmm.
If we don't end up doing that, I've toyed with the idea of actually using neural networks to do these predictions, but there's a decent amount of overhead work that would need to go into that. So we're still thinking about that. Not sure if we want to go that direction, but using neural networks is probably, if we chose to go that route, probably what we would do.
Okay. And when you say overhead, what are you specifically speaking of? Computational, or the effort that goes into just learning, how to build out the models, or what?
I would say the effort going into building the models, because the way in which we turn our system into features really matters a lot. And that's a really very active area of research in the field right now. But it requires a lot of intuition, a lot of luck, and a lot of time to fit these models well, especially when we're looking at search spaces as large as ours.
Well, Kevin, thanks so much for taking some time to share with us what you're working on. It's really cool stuff.
Of course. You're welcome.
All right, everyone, that's our show for today. For more information on Kevin or any of the topics covered in this show, visit twimlai.com/talk/238. Remember to enter our AI conference ticket giveaway at twimlai.com/AINY giveaway. And of course, as always, thanks so much for listening, and catch you next time.